Now we look at the content level of the concept, that is, the worldly content that the concepts represent. Regarding the concept form, we had seen that there are differences in the degree of formalization, such as in the different representations of objects through art, language, or mathematics. Concepts in general and in a larger composite structure, world concepts or worldviews, occur in different modes of existence, that is, forms of consciousness. And with regard to the development and change of these forms of consciousness, we have looked at the various differentiation processes. All forms occur in different levels of abstraction, that is, each type of formalization mentioned above also has different levels of abstraction. The increase in abstraction at the site of concept content means that increasingly general content can be recognized and represented. To consider this process, we address the following topics. First, we look at the history of the concept of infinity in mathematics, which was first only potential and later actual. Second, we consider Cantor's results on the actual infinity, the hierarchy of the R-levels that make up an infinite number of different infinities. Third, we deal with two fundamental problems of classical mathematics, namely Russell's paradox and the continuum hypothesis. Then, in addition, we treat Gödel's incompleteness theorems as a short parenthesis, which provides general information about the limits of formalizability and the relationship between the content level and the formal level. And then the further development of set theory through the concept of classes is worked on. Building on this, we deal with the general connection between reality and mathematics and Gödel's views on the need for new concepts for the foundation of mathematics, for which we also deal with the Ackermann's principle as an axiomatic basis and the reflection principle. Finally, we consider Gödel's ontological proof of God and the connection between this and the other results. With these results from the previous course chapters, we now come to the nature of the continuum. We can consider the power of the spacetime continuum, which we will also call the homogeneous continuum in the following, in relation to its mathematical description, because mathematics is a projective description of nature, as we had seen in the previous course units. To do this, we look at the development of the mathematical description of infinity and the continuum. In antiquity, any actual infinity was excluded from mathematical considerations, and only potential infinity was allowed, which is very explicit, for example, in Aristotle, and is still the case today in many philosophical and scientific considerations. However, despite this, the continuum was viewed as homogeneous, that is, actually continuous. The infinite divisibility that this actually implied was simply excluded by linking the division to the consideration of the acts of division and not to the actual divisibility. With Leibniz, the consideration of infinitesimals, the infinitely small, was added. Georg Cantor then developed the mathematical consideration of actual infinity and found that there is a hierarchy of infinities, that is, an infinite number of levels of actual infinities with different cardinalities. These are the transfinite numbers. So let us take a closer look at these infinitely many actual infinities, the hierarchy of R-levels. The transfinite numbers form the current system of modern set theory. Cantor's development made an ever deeper consideration of the continuum possible, and this consideration became actually infinite and transfinite. However, Cantor excluded the infinitesimals from consideration and identified the continuum with the real numbers, which was equivalent to decomposing it into discrete elements. Excluding the infinitesimals is unnecessary when transfinite actual sets are permitted, and in addition, not correct for existential reasons. The infinitesimals remain legitimate mathematical objects whose internal structure can, like that of the reals, be infinitely expanded through higher differentials. The real numbers can be expanded inwards and outwards, for example to the hyperreal and surreal numbers. In addition, identification with discrete elements raises some problems, such as Russell's paradox and the continuum hypothesis. Russell's paradox consists of the problem that in classical set theory, with the strict limitation to the concept of sets, the domain V of all sets could not contain itself as a set if V were taken as a set. Therefore, it could not be the set of all sets if it does not contain itself. This is the paradox. The continuum hypothesis concerns the cardinality of the continuum and the question of whether the cardinality, that is, the cardinal number of the real numbers, which are uncountably infinite, follows directly after the cardinality of the natural numbers, which are countably infinite. Assuming this is the special continuum hypothesis, or just called the continuum hypothesis CH. The general continuum hypothesis GCH is then the assumption that this relationship between the cardinalities of the number sets can be established in a general way. In general, the cardinality of a set is smaller than that of its power set. This is the Cantor's theorem. We can create a power set from any set, which is the set of all subsets of a given set. These power set operations result in the hierarchy of bets. We can contrast this with the infinite hierarchy of cardinal numbers. That is the cardinality of the sets and called the hierarchy of the Alephs. The general continuum hypothesis then states that these two series are equal, which means that to all ordinal numbers alpha it applies that Aleph alpha is equal bet alpha, which means that for all alpha it is Aleph alpha plus 1 is equal to 2 to the power of Aleph alpha, because 2 to the power of Aleph alpha is the power set operation. It has been shown in different proofs that the continuum hypothesis can be both confirmed and refused. In his proof sketch from 1939, Gödel showed that the general continuum hypothesis GCH, and thus also the special one, and the axiom of choice AC are relatively consistent with the other axioms of the Mello-Frankel set theory. The axiom of choice is the assumption that there is always a possible order in all sets, even infinite ones, so that F set theory remains consistent with the addition of the axiom of choice and the general continuum hypothesis, or it is already inconsistent if that F it is. Then we get from Cohen's proof from 1963 via the forcing method that AC and GCH do not follow from the remaining axioms of that F. That is, that on the basis of that F, neither AC from CH nor vice versa, so CH from AC follows, which also includes the GCH. This means that AC can hold in that F, but CH cannot be proven from it. From this we get as a result that set theory is possible with and without the axiom of choice and the general continuum hypothesis, and that there is no uniform foundation of mathematics on the current axiomatics of set theory, and that on the basis of the existing axioms there is no general order for the infinite levels of infinities. That means the systematics of set theory remains coherent if one assumes no further numbers between the cardinality of the natural and the real numbers, as well as an infinite number of further levels of infinities. This shows that the decomposability of the continuum can be continued in any way. The order of a set of numbers, for example natural or real numbers, is only an observation in certain proportions. In addition, we briefly consider Gödel's incompleteness theorems and can summarize the main results. Firstly, this is Gödel's theorem 6, which he calls the general result about the existence of undecidable theorems and on which the further results are then based. There he first shows that in the system P he set up for the proof, in connection with a certain consistent recursive class of formulas, there are primitive recursive formulas of which neither their statements nor their negation can be proven. Based on this theorem, he addresses the connection between incompleteness and infinity in a footnote, namely, the real reason for the incompleteness of all formal systems lies in that the formation of ever higher types can be continued into the transfinite, while in any formal system there are at most countably many. Then we get the first incompleteness theorem, which says, in each of the formal systems mentioned in Theorem 6, there are undecidable arithmetic statements. And the second incompleteness theorem reads, no formal system that has at least the expressive power of P can prove its own consistency. The results from these theorems are that there is no ultimate foundation of mathematics in today's axiomatic way, and that there is a connection to infinity via the constant expansion through new axioms. Now we look at the further development of set theory through the introduction of classes. Classes were introduced as a new concept, and the distinction between sets and proper classes as a basic element of NBG set theory, that is the von Neumann-Bernays-Gödel set theory. We can define classes as follows. A class X is called a set if there is a class K with X element K. A class K is called a proper class if K is not a set. Among the classes of NBG set theory, there are sets as exactly those that can have an element relationship to other classes. Proper classes are then those that cannot themselves be elements of other classes. The introduction of this new term solved Russell's paradox, because the origin of the Russell's paradox is to regard the area V of all sets as a set. In NBG, V is instead a proper class, namely the universal class, and due to the class concept it is unreachable for any set formation. Gödel wrote, the structure of set theory with V as the universe of all sets and as a proper class corresponds to a maximum principle from which the axiom of choice follows. This means that the universal class remains unattainable, but orders are always possible within it. From this we can conclude some results. The mathematical continuum can be arbitrarily expanded, but it is not completely captured by any of the sets of numbers. In mathematics, points are treated as indivisible, that is, discrete, and are therefore understood atomistically. However, indivisible points can only produce something discontinuous, since they only appear as boundaries of something continuous and do not themselves have their own existence. See second argument from above in part 1. This results in some problems for mathematics, namely, the irrational real numbers are treated as indivisible points, but are each an infinite process, not a discrete point. The distinction between placed points only becomes possible when we assign numbers to them or project coordinates into space, but coordinates and number series are both projections. They do not exhaust the continuum. There are always any refinements or extensions possible and always options for new projections. The homogeneous continuum is the basis for these projections and therefore, as a necessary prerequisite part of mathematics that cannot be excluded. Gödel wrote about the inaccessibility of the universal class. The universal class as the universe of all set V is absolute infinity. This inaccessibility of the universal class should be the meta-theoretical foundation of mathematics. He calls this the Ackermann's principle as the first fundamental axiom of all further axiomatics. V, the universal class, is unattainable. Furthermore, this inaccessibility of the universal class results in the need for a new meta-theoretical concept of sets. Because, as a consequence of absolute infinity as the basic axiom, we get that essential properties of proper classes are retained but transferred to sets, which is also called the reflection principle. This makes closed intervals, limited sets, and points themselves absolutely infinite. We take a closer look at the Ackermann's principle and the reflection principle. As mentioned above, the Ackermann's principle, that is, the unattainability of V, should serve as the basis for all other axioms and principles. Gödel writes, Ackermann's system is based on the idea of the indefinability of V, or the absolute, and all the principles for setting up the axioms of set theory should be reducible to a form of Ackermann's principle. The absolute is unknowable. The strength of this principle increases as we get stronger and stronger systems of set theory. The other principles are only heuristic principles. Hence, the central principle is the reflection principle, which presumably will be understood better as our experience increases. This means that every axiom of infinity should be derivable from the principle that V is indefinable, in the sense of a final structuring. And in the second quote, he already makes the reference to the reflection principle. The reflection principle states in set theory, on the one hand, that it is possible to find sets that correspond to the class of all sets with respect to a certain property, that is, they are reflected by it. And on the other hand, that it is not possible to structurally completely grasp the universe of all sets V with a classical concept. Gödel writes, the universe of all sets is structurally indefinable. It cannot be uniquely characterized, that is, distinguished from all its initial segments, by any internal structural property of the membership relation in it, which is expressible in any logic of finite or transfinite type, including infinitary logics of any cardinal number. The totality of all sets is, in some sense, indescribable. When you have any structural property that is supposed to apply to all sets, you know you have not got all sets. There must be some sets that contain as members all sets that have that property. The connection between the Ackermann's principle and the reflection principle is that the unattainability of the absolute can be seen as a fundamental reflection principle. For example, the property of point sets and subsets of a straight line is that the straight line can be covered by an infinite number of intervals of any length, which applies to every line, that is also to the newly created line pieces. Here we see the reflection principle, since the power of V is mapped to arbitrary subareas. Regarding the properties of the line, Gödel further describes, summing up all the points, we still do not get the line. Rather, the points form some kind of scaffold on the line. The line cannot be captured by the point continuum. Overall, however, the indescribability and unattainability of V can only be understood in a structural and not in a general sense, since the absolute infinity has already been recognized as the most general level of content and is also kept conceptually covered by the concept of the universal class. Building on these results, we can derive a general connection between reality and mathematics. In part 2, we already looked at the indispensability principle, which describes the necessary realistic anchoring of mathematics. Gödel was strongly oriented on Leibniz's monadology. His goal was to build an overall system of science, to find an exact theory of metaphysics, presumably in the form of monadology. Monadology, in turn, is structured in such a way that everything emerges from the primordial monad, which is God, and which is explicitly described as absolute infinity. After that, all other monads are added for the structure of the world. We find this connection analogously in the relationship of the absolutely infinite homogeneous continuum to the point continuum of sets, or the universal class to the other sets and classes. The necessity of this connection follows from the existential relationship between objects and their constitutive background, which we find in the figure ground separation and in the relationship between being and entity, which we discussed in part 1. This relationship results in a fundamental ontology, which Gödel calls the relationship of causality. The new terms, such as the Ackermann's principle and the reflection principle, are intended to solve the problems of the axiomatic foundation of mathematics, such as the problem of the special and general continuum hypothesis. For this purpose, a new concept of sets can be developed that regards the continuum as homogeneous. This results in an expansion of the discrete mathematical continuum to the homogeneous continuum of absolute infinity, which is the existential background for the systematics of the discrete point set continuum, that is, all arbitrary infinite sets and their extensions. This corresponds to transferring Gödel's concept of the universal class with its properties, such as the Ackermann's principle and the reflection principle, to the concept of the today's mathematical continuum. And this gives rise to the new concept of the homogeneous continuum, because the homogeneous continuum is the basis for the discrete mathematical consideration. As a consequence of the Ackermann's principle for the consideration of the continuum, we receive the continuum to be absolute infinity, and that means that absolute infinity is reflected in every point, hence every point is itself absolute infinity. Through the connection between mathematics and reality, the absolute infinity of the universal class corresponds to that of the spacetime continuum. Absolute infinity is the necessary projection basis for all mathematical and space-time considerations, and the necessary basis for structures to exist at all. Transferred to being, it forms the area of being in which every possible existence occurs, that is, the most general being of every entity, whereby, as the most general area of being, it is not conclusively defined. It just has to be determined to a certain extent in which area we operate by distinguishing common characteristics from others. Now we can finally consider Gödel's ontological proof of God and the connection between this and Gödel's other results. His proof of God lies within the tradition of ontological proofs of God, which draw conclusions from the logical conceptual level to the level of being. In this tradition, God is generally defined as the maximum than which nothing greater can be conceived, that is, as the absolute maximum. On this basis, Gödel defines God as the being who has all, in other words, the maximum of positive properties. Here we find again the concept of absolute infinity, which, together with the Ackermann's principle, formed the basis of set theory. In order to carry out the proof, Gödel then defines positive properties in the basis as the simple, that is, not composite positive property of being or existence. This corresponds to his fundamental ontology of causality, and this applies to all tensors, spatial forms, and possibilities, because with Gödel there is no independent spacetime frame assumed. For him, all times and possibilities in spacetime are always present. That means in order to be able to make the inference to the level of being, the maximum of being must be highlighted to receive the maximum of positive properties. The consistency, that is, the validity of Gödel's ontological proof of God, was proven in 2013 by Bensmüller and Paley. And as a connection between Gödel's works discussed before, we see that he proved the concept and existence of absolute infinity through the conclusion of the proof of God, which in turn was derived from the opposite direction as a necessary condition or prerequisite in set theory. That means we get the conclusion of equivalence. This brings us to the end of this third part, and you can find here the literature used and recommendations for further reading.